Okay, radiotherapy is quite interesting. Here's a plug for the physics side of things. Is one of the original targeted cancer therapies. And our business in radiotherapy is treating localized disease. And you all know that it starts relatively small, a few millimeters of disease, and then it starts to grow its own capillary system and becomes a tumor. And then when it becomes a little bit older, it starts to leak. And of course, you get metastasis and you get spread of the disease alongside the invasion as well. So that's our business in radiotherapy, localized cancer. A little bit of history which reflects my life actually in a way. I started out in radiological imaging, and because I was interested in computers and driving machinery and making devices, I was then asked to go into radiotherapy years ago when CT scanners first came in, and I'll talk about that. But the original hardware, much of which we still use in one form or another in imaging, involving X-ray production, goes back to 1895, of course, with William Röntgen, who discovered these very, very penetrating cathode rays before they became X-rays. And what's quite interesting is within the space of just a few years, and it's a bit sad, we got two medical disciplines springing up. One was imaging, it became radiology. And shortly after that, we started to use X-rays for treating. And by the 1920s, we had your typical doctor with top hat on, standing next to a patient delivering some radiotherapy, which wouldn't look too out of place if you looked at some pictures from the 1950s. They diverged a little bit later because we're dealing with X-rays at this stage in physics applied to medicine, X-rays which are really what we would term soft, not very penetrating, but they were good enough to get the job done for imaging and to do some superficial treatment, notably in this case, breast treatment. By the time I joined the Christie, we still had a few of these huge X-ray machines we call maxitrons. Sounds like something out of a video game. There were 300,000 volt X-ray tubes, which were used extensively for breast treatment. And one of the key things about X-rays is, you should know this really, I think everybody should know this, it's not the X-rays that actually do the damage, it's the electrons that they release as they ionize the tissues they're passing through. And you can see on the left-hand side, I've put in blue to make it clear where the X-ray is passing. You can see a big ionization wave scattered around this, which is where the electrons are passing through tissue and doing their damage. If I show you a picture of cells against that track, you can see that we've got a lot of interactions taking place as the X-rays plough their way through the cells and they cause damage. This ionization and the way we put energy into a tumour is really important. And that's an attractive thing to say to physicists because one thing we like to do is have more power and more energy. And we've started to do that in radiotherapy big time. What changed? Why did we move away from X-ray tubes to get our photon therapy? X-rays are photons. Well, in the 1950s, we started to use what's called magnetrons, which had been developed in the Second World War. Now we use them in our microwaves to heat our food, but we use magnetrons to make electrons surf down a hollow metal tube, gathering energy, and then we smash them into a piece of metal, a piece of tungsten, to produce very high energy X-rays. And that formed the basis of the linear accelerators, which we see today in all our cancer centres. And again, I'm old enough to remember a machine like this one, the one that's in black and white. We actually did see in colour in those days, it's just that we didn't have the right colour film. Our machine at the Christie was unique because it was blue. And I think it had something to do with the hospital support for Manchester City because it was the exact same colour of that team. But it was exactly like this, and it was very intimidating for somebody from diagnostic radiology who'd been used to a small X-ray tube to walk into a room like this, and I was a physicist then. I hate to think what it would be like for the patient to see this kind of machine. But these are the linear accelerators of the past. What we had to do quite quickly in physics is try to engineer the patient into a properly systematized treatment planning approach. And that really only became possible with the dawn of the computer era. Again, if I can use my age as leverage, when I first joined radiotherapy, I was becoming interested in computers. I'd done astrophysics at university, and computers were the norm. When I went into radiotherapy, we had a lady called Barbara Brooks, very grand, who meticulously drew out with acetate sheets depth dose curves, and then every single plan had to be hand watercoloured to show the high doses and the low doses before our doctors would actually use it for treatment. And they told me that I had to make computers do it instead, which is what I did. And it coincided when I went in with the advent of CT scanners. Now, the Christie was unusual amongst most hospitals. Most hospitals took CT scanners. Hounsfield, famous British physicist and engineer working for EMI, they make records as well, and Cormac, who was eventually at Tufts University in America, they produced a machine that could see inside without any spurious detail. And the machine that we had at Christie looked like the one you can see on the right-hand side at the top, but it wasn't in diagnostic radiology. We bought our body scanner exclusively for radiotherapy purposes because we realised that we really did need to see what we were treating. And this was a really big thing for us. And to be able to see X-ray projections turn into inside pictures of the patients like this, these are just X-rays going through a patient in one's plane, and when you fire them and put them back together in a computer, they make very interesting pictures like this. They're called cross-sections, axial cross-sections. I spent about 3 months of my life programming one of these, feeling really, really pleased with myself, and of course they became the norm within a matter of a few years. This is me in younger days, standing by one of our next generation CT scanners. And one of the things we could do in those days is be real physicists and engineers. We could actually tinker around with things inside the scanners, take the covers off and run them without the covers. Health and safety wouldn't let us do that at all. We would even have groups like yours come round into our CT scanner department, and we would take the great big covers off and say, stand a bit closer so you can see it and get the feel of this thing rotating round, several tons rotating in 1 second. Well, what did we do? We started using this for radiotherapy planning. Lots of salami slices, cross sections, making a 3D volume. We then got into things like dose model generation. It's good if you know mathematics and if you know a bit of physics, a bit of computing. You can put them together, and on the screen you can produce things like this. I wrote a treatment planning system for intracavity therapy when I was young. And then I worked with the university, a guy called Richard Hubbold, and we thought, since we're generating 3D images, why can't we see them in 3D? And we started to do the kind of displays that you're now used to when you buy your Panasonic 3D television system. We had a mock-up of that in one of our planning rooms, and it looked like this. But of course I can't show it in 3D because we can't project it 3D. And everybody thought this was wonderful. We could actually predict to a 0.5 millimetre where the radiation was going to go and how intense it was going to be, how much dose it was going to deliver. And that's these red blurs. The bottom blue bit is meant to be the rectum. The green bit is the prostate, and above that we have a bladder. So this is a typical pelvic type treatment. The problem is our treatment planning hardware, software, visualization, accuracy wasn't matched in the treatment room. We still had rather slicker versions of those linear accelerators, but nevertheless we still used very large lead blocks on motors. You can see them, they're called collimators, which moved in and out, 2 pairs, an X set and a Y set. And that meant, although we knew an awful lot about our patient to the millimetre, we could only treat a brick. And tumours don't come in brick shapes. We referred to this kind of treatment as a brick treatment. And in the States, and in some hospitals that were particularly well off, they were using custom blocking. They weren't just using lead blocks, lead collimators. They were using custom blocking to change the shaping of their treatment beams to match those of the patient. We did something a bit differently because we were a bit mean in the Northwest. We decided what we would do is work with Philips, who had a manufacturing base in Crawley, on the design of what's called a multi-leaf collimator. Slivers of tungsten, each one driven by computer control, to make nice shapes, individualized shapes, so that we could fire shaped beams at the target in our patient. So, 1993, we were doing custom-shaped, individualized, targeted treatment, something that our biopharma colleagues are still trying to do with their drugs, which is quite interesting. This type of beam shaping became so successful that almost every linear accelerator you can find now has a multi-leaf collimator on it. And treatment planning became systematized, with the ICRU organisation in 1993 issuing a set of rules and guidelines for our clinicians to follow in oncology. One of the early plans that we developed, this is a graphic that I programmed personally, so that we could actually shape the collimators to 4 different angles around the patient and then deliver it to them. And then deliver it to them. To what? We have no pictures of our patient in the treatment room. Now again, I'll use my age. When I moved from diagnostic radiology into radiotherapy and I saw these huge machines, my first question was, where's your mobile X-ray unit? Because even when you're on the ward, you can have an X-ray taken whilst you lie in your bed, with some kind nurses bringing a mobile X-ray unit on and firing a picture, some X-rays through to get a picture. And I couldn't understand for the life of me why we didn't have these in radiotherapy. We didn't. What we did have is the megavoltage portal imager, which produced pictures like this. And if you're very clever, you can use a graphics pen and you can trace out there a bit of the pelvis. And that's what we were left with. Exquisite treatment planning, exquisite beam shaping, but actually what we were doing, at the moment of treatment, we were putting the blindfold on and throwing the knife. And that really was quite worrying. We really need to aim before we treat. And so we very quickly got into research agreement with Philips' successor, Electa Oncology Systems, when they asked us if we would like to look at in-treatment imaging, what you call image-guided radiotherapy. One of the first things we wanted was to be able to do fluoroscopy on our patients. Okay, if you actually rotate our X-ray tube, which is strapped onto this linear accelerator gantry, around the patient and keep it on, you can see that we can get a rotation fluoroscopy sequence. And you can probably see that that patient was keeping perfectly still, but they were not actually keeping perfectly still. They were jiggling around. That's natural physiological motion that you just simply can't stop. And at this point, we got involved in another project. Fluoroscopy was one thing. We could take some X-ray pictures of our patient, which was fine, but it would be a lot better if we could actually do something far more exciting and introduce what was called cone beam CT imaging. Cone beam CT imaging is where you keep the X-ray fluoroscopic pictures on, and you can see in this particular patient we're rotating the X-ray unit around the patient. Don't forget this X-ray unit is actually attached to the linear accelerator gantry, so it's got the same mechanism for moving. So we've rotated the gantry around the patient, and we've taken the fluoroscopic sequence here, and then we can reconstruct an image literally in one ear, through the head, and out the other ear. And what that did overnight in 2003 is propel radiotherapy ahead of radiology, because we were able to see in the treatment position a patient with 1 millimetre accuracy in all directions. So we could have 1,000 by 1,000 by 1,000 points of our patient in exquisite detail at the point of treatment. Very, very quickly, this became the standard of treatment, image-guided radiation therapy, which the government, the Department of Health, aspired to. We're now moving towards image-guided adaptive radiotherapy, where because we can see how the tumour is day to day, treatment to treatment, we can ask ourselves, do we want to make some kind of intervention, or as one of my colleagues has done, a younger colleague, makes those images fit for direct treatment replanning without the need to go back to the CT scanning department for a standard CT type scan. There is another problem. We jiggle on the inside and we jiggle on the outside. And certainly when we were engaged with David Ardron and the consumer groups that we've come to know quite well, we asked what was one of the single biggest problems from the patient's point of view. And it is being left alone at the moment of treatment, because the radiographers and the physicists will say, don't worry, it's fine, and then they slowly sneak out and they say, we can see you in that camera up there, but you're on your own. Now, certainly when I've had an MR scan, I was told a few years back, please keep still. What does that mean? What does that mean, and how do you know, did you keep still well enough? Well, what we've done is we've taken some clever optical technology, projecting stripes. They look like stripes, they're actually wave patterns onto our patients in red, green and blue. And we were able to produce surface images, this is the abdomen and lower chest area of our patients using this. And now we can do it so fast, you can see my young assistant, this is James, bearing all for your entertainment. This is real-time imaging of James on the treatment couch, stripes being transformed into a 1 millimetre accuracy, three-dimensional model of him. He's being acquired, he's moving deliberately, and what he's wearing, you can't see, is a set of straightforward video glasses, the kind of things that your sons or daughters might be using on their gaming stations. And the result is we can take this kind of data and we can feed it back to our patients, and we can just show them a traffic light picture of how they should or shouldn't be moving. Red means you shouldn't be moving that much. Try and breathe little less deeply. Just try and keep within the amber and the green area. And we've just finished a short clinical volunteer trial, and wearing these glasses was very, very well received, and we got much better compliance with movement tolerances, which we hope we can take forward now into a proper patient study. The advantage of this is that there's no radiation dose. We can use it on demand anytime we like. So, state-of-the-art photon therapy. I'm trying to move people away from X-rays to photons. X-rays, radiation, etc. have historical connotations that are not so good. What armoury do we have? Well, we have a really amazing armoury. We have Elekta, which I've just talked about, and the Varian in the States. They're Linac with imaging on board, the image-guided radiotherapy. We have tomotherapy, where they put the linear accelerator on the CT scanner, and they rotate those together. And we have separate C-arm mobile X-ray units which can be rolled into the treatment room and can be used with a linear accelerator. And Mitsubishi Heavy Industries in Japan have come up with a radically new design. This is the Vero system, which I don't think any of us could actually afford, but nevertheless it's an all singing, all dancing, moves in all directions type of linear accelerator on a gantry. So I think as of now, we have taken the blindfold off in radiotherapy. We can plan, see and treat with that millimetre accuracy with photons, with your X-rays. I think it won't be very long before we see an array of equipment in radiotherapy centres which is not too different from the surgical theatre. Things will be hanging from the ceilings, on rails, and you'll be able to move around with robotic arms almost everywhere. This is a cyberknife, which is used in neuro work. So we've come a long way, all because of computerization and because of physics. But of course, it hasn't stopped there. If photons are not so good, how about protons? Now, protons are quite interesting. They're like electrons. And these big machines that you've already heard about really are like slingshots. When I was a kid, I used to get a cereal bowl and put a marble in the middle of it, and I would do that. And the marble would roll around. Then it would get perilously close to the rim of the cereal bowl, and my mother would say, "Don't do it anymore because it will fly off and it'll break my mirror." And just as you said that, it would fly off. Now that's exactly what you're doing in one of these big magnets with an electric field, occasionally giving the protons a push, a push, a push, until eventually they fly off. And they have so much energy that they can penetrate a long way into the patient and then suddenly lose their energy, as you've heard before, in a quite precise fashion, without going all the way through the patient. And that's the big thing. X-rays go right through you, protons don't. And you've seen this picture before. This is the inside of one of those machines. You can see all the magnets that are involved. And this is one of the bigger gantries. This is the gantry for a proton machine. I was at a meeting in Manchester late last year when our German colleagues from Heidelberg, which is the ion beam facility, proudly announced they have the biggest gantry, weighing 250 tons. Well, we don't want massive gantries. We want to be able to deliver treatments that go in and don't come out, producing additional healthy tissue dose. So what's on the horizon already? Just as we're moving into a national proton therapy capability, there are compact proton machines being designed. In the United States, Lawrence Livermore have teamed up with Rock Mackey in tomotherapy to propose the idea of a radically new accelerator called the dielectric wall accelerator. It's got problems, but it's still a potential design. And in the UK, at Daresbury, Professor Parker has actually been working on this, the EMMA accelerator, which, although it still looks big, is relatively compact, and of course it can do more than protons. And what about the future? Things are moving really quickly. We had image-guided radiotherapy from 2004 onwards. We're only in 2012, and we're moving from protons and thinking about something else in the physics community. Another thing that you should know about X-rays. I talked about the electrons that do the damage as the X-rays pass through you. That's photon therapy. When you get to really high energy photons, megavoltage photons, the X-rays come into the tissue, but they don't necessarily produce the ionization in the traditional way. And a chap called Dirac told us something quite interesting. When a high energy X-ray goes through the body, it produces antimatter. In fact, it disappears, and an electron and an anti-electron, a positron, actually appears. Sounds a bit Trekky. This was the antimatter generator in Star Trek. But in 2006, researchers at CERN did have results from a successful experiment on the biological effects of antimatter on living cells. And when they were looking at antiprotons, they found it was 4 times more effective than a proton beam. So if people are already doing experiments in 2006, it's that twinkle in the eye. And as soon as you have something as a concept, it might become the reality rather faster than you expect. So, in conclusion, I think you ain't seen nothing yet. The revolution is just beginning. Thank you.
Thank you, Chris. Superb lecture, starting off with the Science Museum and moving into tomorrow's world, yes. Vision of the future. The problem with that antimatter machine, I believe, is that it might work on you, but then you dematerialize and appear on another planet. You're still working on that. But the perfect person to fix it. Right, time for questions for Chris.
I'd like to ask you one. I know the proton beam is a new modern technology. I'll have to be doing some read upon it myself on the computer. It actually starts, let me say, in the States, and hopefully we will get it into the UK sometime, hopefully in a smaller version from the original one, which was built in an aircraft hangar, if memory serves me right. But what is the future for the proton beam? Will it be also used in all types of cancer, or will it just be in specialised treatment like brain tumours?
Well, my personal opinion is that there are very cheap, compact proton generators, machines actually coming along. In principle, they're already there. It's in practice that they have to be proven. Now, there's a Russian company called Proton, which have signed an agreement with an American company based in Houston to produce the Proton compact machine. Now, I think that's about to get FDA approval, if it's not already got it. So I think we're in an era where we will suddenly have relatively cheap proton therapy machines available. And that's why I put those slides in. Maybe we're seeing a paradigm change. Just as we moved from the X-ray tube to the linear accelerator in the 1950s, we may just be on the verge of moving away from photons to a very large admixture of protons. It will be a mixed modality. We'll have photons around and we'll have protons. But protons, I think, will become much cheaper and much more controllable than they currently are. So yes, I think protons are the future, much more widely available.
Fascinating.
One is politicians comparing our cancer survival rates with those of other countries, often negatively. How do we, with the developments that you've been talking about, how do we compare in what we offer patients in terms of radiotherapy in this country with, say, Germany?
Germany in particular has always been a little bit more forward-thinking than the United Kingdom in terms of its hardware provision. And I think in terms of the risk it was prepared to take to advance the state of the art. Holland is the same. But I think it's a mistake to think of Europe as some kind of homogenous group where they're very much more advanced than we are. I would characterise our approach on protons as probably just about right. It was best to let other people take machines from the nuclear labs, and in some cases, certainly in Boston, their first proton machine was a cast-off from MIT on the other side of the Charles River. I think it was better to see that technology mature than to jump in with both feet, given that the cost is so high. And I think even if we get the current state of the art of the technology in, and we find proton compact systems are in which are cheaper, then at least we will have learned how to do it clinically and also technically. The technical effort to keep proton machines going is absolutely huge, and we need that experience now. I would probably suggest that it might be nice if UCLH and the Christie, their first machine was one of the big machines, and their second machine was a compact machine, and then we could literally roll out proton therapy to other centres who needed it. Does that answer your question?
Thank you.
With a bit of luck, Sheffield will get one when they're about suitcase size.
Oh, it's nice to see you again. I'm just thinking, you just said it'd be nice for the Christie to get a big one. Thinking about the site, just exactly where you intend to put it. You might as well go and use the one at Daresbury. It's probably the only place you could get one in.
Well, in fact, on the other side of the road, Christie is between two main roads, which is Palatine Road and Wormslow Road. Christie is fortunate in owning a lot of land on the other side of Palatine Road, which you can't see from the main road, but is basically a surface car park, which is absolutely enormous. So that was the first place that we thought about putting that. But it's also been the case that the plans are now to put it on the main site. We still have enough open area around the periphery of the hospital to put a proton therapy site. So space is not one of the problems in Manchester.
I was going to say, don't mention it in the car park.
Well, I'll let you into a secret. We did plan a multi-storey car park with several levels, and that became a multi-storey car park with one level,
Yeah.
as in a ground car park.
More questions? Chris, can I ask about, we've heard quite a few talks today, including yours, about being more sophisticated at delivering radiotherapy from outside into very specific parts of the body. What about the opposite way of looking at delivering radiotherapy from within the body using, the techniques of brachytherapy, where you actually put radioactive sources? I know that's not your field, but can you give us a view of where that sort of approach has gone?
Well, the first treatment planning system I actually wrote was brachytherapy, and
You have to do that as well.
that was based upon imaging, and I think it's prostate, of course, you have ways of actually inserting needles through templates into men and leaving the sources there, and of course they then can go home and the radioactive material does its job. I suppose targeted radiotherapy using radionuclides is something that we're very, very keen to do at the Christie. I know it's not brachytherapy in the sense that you put little lumps of material that emits radiation, but you actually inject a radioactive material. Everything I think would be feasible except for one thing. Although we have treatment planning facilities, computers, nice programs for X-ray, photon therapy, electron therapy, and proton therapy, although they're a bit embryonic. But what we don't have is a treatment planning facility for radionuclide therapy, where you can actually say, yes, this is how the drug will be taken up, this is how the radiation will be distributed with time, and yes, we can combine it with radiotherapy. A colleague of mine, Jill Tipping, is working on that with Tim Illich, who is of course active through the NTCRN-CRP. So that's the next stage.
Excellent.